All right. So today we're going to continue to look at boundary layers. So boundary layer is really a very deep topic, and we won't really get to the bottom of it in 16100. And there is actually a whole subject on viscous flows in the graduate curriculum. And that class is really going to teach you more about boundary layers and viscous flows, and especially how to predict things quantitatively. In this lecture, we won't really do things quantitatively, but what we are going to be doing is to give you a qualitative understanding of how boundary layers respond to both pressure and viscous forces. So you are able to know the trends, and you will be able to interpret what comes out of a computational software like a CFD or Xfoil, right? And be able to make a directional change on the shape of the airfoils to either promote or promote what you want or get rid of what you don't want, right? So the goal is to qualitative understanding of if you change this, that's going to be more likely to happen. Okay, so that's basically the goal of today. And so let's first review what we get to at the end of the last lecture. We described several different metrics, right, of how do we quantify the boundary layer. And today we are going to first review these metrics and then look at how these metrics are going to respond to pressure forces. So we are assuming a boundary layer that has a certain profile, and this is usually how we draw the profile of a boundary layer. The x direction is the velocity along the wall, so the velocity parallel to the wall, and the y is y, the distance away from the wall. So at the y equal to 0, the velocity is also equal to 0. And when y is outside of the boundary layer, the velocity is equal to what we call UE, the velocity at the edge of the boundary layer or outside of the boundary layer. And the boundary layer goes, in a general boundary layer, it goes smoothly. And we'll say in a little bit later why the boundary layer tends to be a smooth profile. But in this particular problem, let's assume at outside of the boundary layer, when y is greater than 1 millimeter, the velocity is equal to 1. And in this case, the UE is equal to 1, right? And in the outermost layer, the velocity is equal to 0.9. And that's all the way it goes to 0.7 millimeters. And then in the more inside layer, the velocity is 0.7. That goes all the way to 0.3 millimeters. And then in the innermost layer, the velocity is 0.4. So we are assuming basically a stair-step profile of the boundary layer. And I want to ask you, what is the 99% thickness of the boundary layer? Yeah. Where did I derive the point? Oh, so this is specified by the problem, right? So we are given a boundary layer profile that is like that. The 0.7 is it's 0.6. Sorry. Yeah, thank you. So yeah, that's 0.6 and 0.3. Yeah, that's right. So the first question is, given that profile, what is the 99% thickness of the boundary layer? Just to remind you, the 99% thickness is the distance away from the wall such that beyond that distance, the velocity is less than 1% different from the edge velocity, right? Or the velocity gets, it's 1 millimeter, correct? Because in this layer, the velocity is still 10% away from the edge velocity, right? Only when you go above 1 millimeter, the velocity is completely equal to edge velocity. So the delta 99 is equal to 1 millimeter. So that's basically according to the definition, right? This is these questions are all answered by following the definition. Second one is, what's the displacement thickness, delta star, as defined as an integral from 0 to infinity of 1 minus u over ue times dy. Right. So in the last lecture, we did the analysis showing that the displacement thickness is actually how much the existence of the boundary layer is displacing the streamlines away from the boundary layer. Right. Okay. And again, according to the definition, this integral can be split into 4 parts. The first part, let's start by the outermost layer, right? The first part. The first part, what is inside the parentheses? It's 1 minus 90%, right? In the first layer, the velocity is 90% of the edge velocity. So inside of the parentheses is 0.1 times dy. What is the dy of that layer? It goes from 0.6 to 1, so times 0.4, right? Okay, and then in the second layer, the difference of 1 minus u over ue is what? What is inside the parentheses? Yeah. Yes. 0.4. No, in the second layer we have 0.7 meters per second, right? Inside of the so u is 0.7, ue is 1, right? So what is in the parentheses? 1 minus u over ue. 0.3, right? That's the what we call a velocity deficit, right? How much velocity is how much less the velocity is in the boundary layer compared to outside of the boundary layer. And the thickness of the second layer is 0.6 minus 0.3, right? That's 0.3. And in the third layer, what is inside the parentheses? 0.6, that's right. And outside of the parentheses, dy, again, the thickness is 0.3. Right, so basically by adding them up, I get the 0.04 plus 0.09 plus 0.18, right? And the summation is 0.3, that's 27 and 31. So that's the displacement thickness of this, yes?
Can you go over where you got the numbers again? Just like how you evaluated it?
Yes, so I split the integral into 3 parts, right? So in this layer, we don't have to integrate because 1 minus u over ue is equal to 0. Right? So in the outermost layer, when the integral goes from 1 millimeter to infinity, the integral is 0. So I start with the second layer. When u is equal to 0.9 and ue is equal to 1, u over ue is 0.9, right? So 1 minus 0.9 is 0.1, so that's what happens over here. And because we are integrating over a constant, the integral is this constant times the length of the integration. And in this layer, the length of the integration is going from 0.6 to 1, so it's 0.4. Okay, and similarly in here, inside the parentheses, 1 minus u over ue is 0.3, right? And the length of the integral goes from 0.3 to 0.6, so that's 0.3. Okay. Right. And another way to see this integral is that we are looking at the shaded area over here. Right, so that's actually for any boundary layer profile. It doesn't have to be piecewise constant. We are always looking at the shaded area. That's the deficit, right? That's how much the velocity is different from the edge velocity. So if you normalize the edge velocity so that it is equal to 1, then the shaded area is the displacement thickness. Again, you can do this integral geometrically by splitting this the shaded area into 3 rectangles, either that way, that's what we're doing here, or this way, right, which gives you another way of performing the integral. All right, any questions on this problem? Okay, then similarly, we'll ask what is the momentum thickness? The momentum thickness, theta. In the last lecture, we did the analysis showing that the momentum thickness is actually related to the momentum deficit, right? So that is how much less momentum does the boundary layer have compared to the same amount of flow, basically the same flow in the same stream tube upstream of the boundary layer. So that's going to be equal to an integral of u over ue times this 1 minus u over ue times dy. Okay, so we can, because the boundary layer is piecewise constant, right, has a piecewise constant velocity, we can do the same kind of splitting. Same splitting, except for instead of, okay, and also the second part is actually the same, only that for each layer we get an additional multiplier of u over ue. In the first part, this additional multiplier u over ue is what? Is 0.9, right? So we get another 0.9 times this 0.1, which is in the same parentheses, and times the thickness of the layer, right? Is it clear where these three numbers come from? The first number is u over ue. The second number is 1 minus u over ue. The third number is the length of the integral dy, right, for the first layer. Okay, and the second part, what additional multiplier we have? We still have 0.3 times 0.3, but that's multiplied by what? By this additional thing, right? What is that? For the second layer, 0.7, that's right. And in the third layer, it's multiplied by an additional 0.4, right? Okay, that's the third layer. And well, I don't think it's worth it to actually compute it, but it's going to be coming something that's a little bit less than that, right? So let's actually just use a calculator. So 0.9 times 0.04 plus 0.7 times 0.09 plus 0.4 times 0.18. If you add them up, it's 0.084, let's say. 0.084. All right. And then finally, what is the shape factor? Right? The shape factor is the ratio of displacement thickness over momentum thickness. So that's basically 0.31 divided by 0.84. So 0.31 divided by 0.84. What we get is, sorry. Oh, yes.
It's not 0.0, it's 0.7. You did.
So I did something wrong. 0.9, sorry, 0.9 times 0.04 plus 0.7. I see. Oh, okay. Okay, let me just do it again. Times 0.09 plus 0.4 times 0.18. Wait, so which one did I do it wrong? Let me just use a browser. Plus, just close this. Plus 0.7 times 0.09 plus 0.4 times 0.18, right? Okay, so I think the calculator has something that that made the order of operations probably not correct. Okay, so 171, and so now I get 0.31 divided by 0.171. So that's my 1.8. 1.8. That's my shape factor, right? Okay. All right. And finally, the last thing we want to compute is what is the skin friction coefficient. And I'm saying approximately because the skin friction coefficient it's CF is equal to the tau, which is the shear stress per unit area divided by half of rho UE squared, right? Okay, and what is tau? Tau is equal to mu, the viscosity, times the derivative of velocity with respect to y. Again, divided by half of rho UE squared. Now the thing is, this is at the wall, at y equal to 0. Now the thing is, if we are assuming a piecewise constant velocity profile, then there is no derivative at the wall, right? So we have to approximate it. We have to approximate it with the understanding that this piecewise constant velocity profile is an approximation. The real velocity profile has to be equal to 0 at the wall. And if you connect this velocity with the average velocity at the middle of this first layer, that's something we usually use actually. So basically, if we have a many, instead of 3 layers, if we have 300 layers, right, then the derivative at the wall can be approximated by connecting the origin with the middle of this layer, right? So that would be, the velocity here is 0.4 and the middle of the layer is 0.15. So du dy is approximately equal to 0.4 divided by 0.15, which is, again, let me just use this one. That's 2.67. All right. So that's something I'm going to plug in, and of course, in here you have to use the viscosity of air and the density of air to plug in for this skin friction coefficient, right? So again, let's just use a rough order of magnitude number. So viscosity of air is 10 to the minus 5, and let's just use a density equal to 1, and then basically we also have 1 meter per second, right, as the velocity. So the denominator is just a half, and du dy. Okay, so this thing has a unit. So we have a meters per second, and here is 0.15 millimeter. So what we get du dy is actually times 10 to the 3, right? Because the millimeter converted to meter has an additional 10 to the 3, 1 over a second. Okay, so plugged over here, we get 2.67 times 10 to the 3. Okay, the skin friction coefficient we get is going to become, let's see, 10 to the minus 2, another 1. So it's about 5.3 times 10 to the minus 2, right? So that's roughly the skin friction coefficient we get. All right, any questions on that? Okay, so let's actually, yes. Yes.
Instead of like whatever you had, like the just 0.4 closest to the wall.
Yes. So in skin friction coefficient, that's a very good point. I look at the tau at the wall, but I don't use the velocity at the wall, because the velocity at the wall is equal to 0. Right? For any continuous profile, the velocity at the wall is equal to 0. And the more layers you use to approximate the velocity profile, the smaller the first layer velocity is going to be. So using the velocity close to the wall is not a good quantity for non-dimensionalization. Instead, we use, it actually depends on situation. So we either use the free stream velocity or the velocity outside of the boundary layer as a non-dimensionalization coefficient for the skin friction coefficient. Yeah. Okay. All right. So now with this in mind, let's just recall these numbers, right? And we'll get back to these numbers a little bit later, because now we are going to look at how this particular boundary layer is going to react to a pressure gradient. And this type of reaction actually will qualitatively be the same for any boundary layers. So let's get to that. Okay, so this is already, let's actually copy these numbers here. 1 millimeter, and we have 0.31 millimeters, and we have what, 0.171 millimeters, and the shape factor is a non-dimensional number equal to 1.8, and the skin friction coefficient is equal to 5.3 times 10 to the minus 2. Okay, now let's actually start by looking at how this particular boundary layer reacts to a pressure gradient. So let's say between over some length of x, right? Some length of x that is significantly greater than the thickness of the boundary layer. I said I said 50 millimeters here just to give a number that's like almost the 2 orders of magnitude greater than the thickness, right? Now we have a favorable pressure gradient. So what does a favorable pressure gradient mean? A favorable pressure gradient means a pressure that is decreasing as the boundary layer travels downstream. All right. So what does a decreasing pressure do to a pressure? To a velocity. By decreasing, I mean decreasing along the direction of the velocity. In a steady state flow, right? If you travel along the streamline and you find your pressure decreasing, what can you say about the velocity along the streamline? It's increasing, exactly. Okay, the velocity will be increasing. So the first question I have is, what velocities will be the 4 layers are? And here, let's make sure we are ignoring the viscous forces, right? Ignoring the viscous forces means the only force you have to consider is the pressure force, right? And also, if we ignore viscous forces, can we use Bernoulli? It's kind of a question. Can I use Bernoulli? The answer is yes and no. Okay. Yes, if I use Bernoulli along a line that does not have any vorticity on it, then yes, I can use Bernoulli. But if I use Bernoulli along a line that crosses some place with non-zero vorticity, then no, I cannot use Bernoulli, right? So in this case, for example, where are the non-zero vorticities? It's here at y equal to 1, y equal to 0.6, y equal to 0.3, right? But if I only use Bernoulli inside a particular constant velocity region, and in particular along the streamline, right, then I'm not crossing anywhere with non-zero vorticity, and I can use Bernoulli. Okay, so let's do that. Let's use Bernoulli in the restricted sense, right? We don't use it across streamlines, but along the streamline. And then let's think about how does the velocity change over these 50 millimeters, right? Okay, so we know that the pressure gradient accelerates the flow to a higher velocity outside of the boundary layer. So what can we say about how much pressure difference there is? And what can we say about how the 4 layers within the boundary layer has increased in its velocity? Any thoughts? Oh, what is Bernoulli's equation? What is equal to constant? Stagnation pressure, which is equal to pressure plus half of rho v squared, right? Okay, so we know P plus half of rho u squared is constant, okay? And that's a different constant for every layer, right? Different constant for every layer, okay? But for every layer, for each layer, my delta P plus delta half of rho v squared is equal to what? Is equal to 0, right? Okay, so that means if I know how much the delta half rho v squared is at the outside of the boundary layer, I can compute what delta p is, right? And the delta p, is it the same for the different layers? Right, so that's actually a non-trivial question I need to answer here. So here we have a flat plate. Let's actually no longer exaggerate the aspect ratio. Okay, so here is the previous boundary layer. Here is the downstream one. The boundary layer is very thin, so it's like that. Sorry. Okay. Yeah, so the boundary layer is very thin and the wall is flat. Okay. Is there any streamline curvature or not? So the streamlines, the boundary layer may become a little bit thicker or a little bit thinner, right? But because the wall is so flat and the boundary layer is so thin, the streamlines are basically straight, right? There is no way the thickening and the thinning of the boundary layer can cause significant streamline curvature. As a result of that, what is the pressure gradient in the wall normal direction? Can only be 0, right? Because if there is a pressure gradient in this direction, it is going to turn the flow, right? Pressure gradient in the streamwise direction is going to accelerate or decelerate the flow. Pressure gradient in the direction normal to the streamlines is going to curve the flow. That's centripetal force. Yes?
How do you know it's the streamlines are straight? How do you know that the boundary layer doesn't increase thickness around the fixed value?
Yes, so it will either decrease or increase in thickness. We are going to look at it a little bit later, exactly how much it increased or decreased. But the thickness is 1 millimeter, right? And the length we're considering is 50 millimeters. So even if it thickens by a factor of 2 or thins out by a factor of 2, right? It is on the order of 1 millimeter over the length of 50 millimeters. So the resulting streamline curvature is going to be very, very small, right? So that is what, it's the aspect ratio, right? The thickness of the boundary layer much, much less than the horizontal length scale that makes the streamline curvature negligible. Okay, so that's basically the geometry. That means there is a dp dy, or let me just say partial derivative, is approximately equal to 0 due to small streamline curvature. Okay, so not only the pressure gradient is small, right, but also the delta y is also small. So by delta y, I mean the difference in the y coordinate of the different layers, the 4 different layers we're considering, right? Delta y is also on the order of 1 millimeter, while delta x is on the order of 50 millimeters. So as a result of that, partial p over partial y times delta y is going to be much less than partial p partial x times delta x, right? So basically, we have this much less than this, and also this much less than this. As a result of this, the variation of the pressure in different layers is much less than the variation of the pressure between this station and this station. Okay? So that means we can pretty much think about this delta P as the same across the different layers. This delta P is the difference between the pressure at one station in one layer and another station in the same layer. Okay, so basically, you can think about the pressure as P0 across different layers, and P1 to be also the same across the different layers. But P0 is different from P1. Okay. So basically, delta P is equal to P1 minus P0. does not is the same across layers. Okay, so this is actually a pretty universal statement for any thin boundary layers. Okay, unless you get to low Reynolds numbers, if your Reynolds number is 0.2, it doesn't hold anymore, right? But as long as your Reynolds number is in the thousands, tens of thousands, hundreds of thousands, millions, you can consider the pressure to be only as a function of where you are in terms of the location on the wall, not where you are in terms of how far away you are from the wall. Okay, so that's a true statement for thin boundary layers. Okay, so now if the delta P is the same and can be computed by the delta half rho u squared on the outermost layer, actually on the edge of the boundary layer, right? That means we can use the same delta P for the different layers inside the boundary layer. And if we know what is the velocity on a station 1, we know what is the velocity on the downstream station. Right? Okay, agreed? Okay, so let's compute it. Okay, so we know that delta, let's say, u squared on the outermost layer, let me just say on this layer is equal to, well, I put a convenient number here, right? The 1.414 is square root of 2, right? So it's actually 2 minus 1, right? So this is because on the downstream location, the velocity u at the first layer is 1.414, and here the velocity at the first layer is equal to 1, right? So that's given here. So the flow has accelerated from 1 to 1.414. So the delta u in the first layer is this much. Okay, that means my delta P over half of rho is equal to, well, that's equal to 1, right? Is also equal to 1. So that's because of Bernoulli's applied to the outermost layer. Actually minus 1, right? Because the pressure has decreased. So yeah, that's minus 1. Okay, then let's look at the second layer. In the second layer, this also has to be equal to 1, right? It has to be something minus, what is the velocity in the beginning? 0.9 squared, right? 0.9 squared. And that velocity has to be what? So let's actually do the calculation here. We have 0.9 squared plus 1, right? And then take a square root. That needs to be what velocity we have downstream on the second layer. So let's just put a 1.3. All right. Is it clear what I'm doing here? Right. This is actually let me just erase this. This is 1.414 squared, right? Okay. All right. So then let's look at what is the velocity difference on the third layer. That also has to be equal to 1. All of them has to be equal to the same pressure difference, right? On the third layer, we have to be something minus 0.7 squared, right? It's 0.7, right? Let me see. Yeah, 0.7 squared. And what has to be the unknown, right, to get to 1? So let's just put a 0.7 here. The velocity has to be 1.2. Okay, and finally, let's look at the innermost layer, velocity at the fourth layer. And something squared has to be subtracted with 0.4 squared to get to the same pressure difference. So let's also put in 4, and it has to be 1.1. Okay, Any questions on why we can compute the velocity at the downstream locations in this way? It's a combination of the zero streamline curvature argument, which means the velocity actually is independent of y at the two locations. The pressure is independent of y at the two locations. That means we can use Bernoulli's to relate the pressure difference with the velocity difference at the outermost layer. Yeah?
What do you use small delta instead of?
Oh, did I? Yeah, I didn't make it consistent. Let me actually use big delta, sorry. It should be consistent. And just use big delta. Okay, yeah. All right. Wait, that's velocity, right? Velocity. Okay. All right. Okay. So now let's actually draw what the profile has changed. So initially, we have, again, let's say we have y versus u, right? Initially, actually, before we can draw the profile, we have to actually answer the second question. How thick are the four layers now? Now we know the four different layers now has evolved from a velocity of 0.4, 0.7, 0.91 into a velocity of 1.1, 1.2, 1.3, 1.4, right? Now, how thick are these four layers? Are they still as thick as before? Are they still having a thickness of 0.3 millimeters, 0.3 millimeters, and 0.4 millimeters? Or has their thickness decreased or increased? Any idea what do we... these are three different stream tubes, right? That travels at different velocities. Now the velocity all has increased. Has the thickness of the stream tube increased or decreased? Decreased, right? That's using what principle? Mass conservation, exactly. And the mass conservation tells us the velocity times the thickness has to be the same no matter if you're looking at a downstream or upstream location, right? So that means the thickness of we don't need to look at outside of the boundary layer, but inside the boundary layer, the second layer has gone from 0.4. Initially it's 0.4, right? It's right. Has gone from 0.4 millimeters to 0.4 times 0.9 over 1.3, right? So that's how much the flow has accelerated. And on the third layer, it has gone from 0.3 into 0.3 times 0.7 over 1.2. And in the bottommost layer, we have the thickness has gone from 0.3 into 0.3 times 0.4 divided by 1.1. Okay, and now if you look carefully at these numbers, you're going to see that the smaller the initial velocity is, the bigger the acceleration is. Is that an accident? Or there is some underlying principle in it? It turns out it's basic mathematics that if the difference in the square are the same, right? Like a squared minus b squared is equal to a plus b times a minus b, right? So if the difference in the square is actually the same, then the bigger the a plus b is, the smaller the a minus b is, right? So that means if the velocity is bigger, right, a plus b is bigger, the acceleration a minus b is going to be smaller. But if the velocity is smaller, the a plus b is smaller, then the a minus b has to be bigger. that's something very interesting about boundary layer, is that the slower the velocity is, the more sensitive is that particular layer to either pressure increase or pressure decrease. So we'll see that as we see adverse pressure gradient, everything is the same except for the left-hand side is going to be a negative number, right? So the sensitivity of a particular layer of fluid actually is inversely proportional to how fast the layer of fluid is. Okay, so the more bottom the flow is, the bigger the acceleration is, and the bigger this ratio, I mean, smaller this ratio is, more close to zero the ratio is. Which means that, let's say, initially the flow is 1, actually 1 outside, right, 0.9, 0.7, I didn't draw it very well. So 0.7 up to here and 0.4 over here. So initially the flow is like that. And after acceleration, the innermost layer, so instead of 0.3, this has gone to basically almost 0.1, right? The innermost layer, and it has accelerated to 1.1. So this is 1.1, this is almost 0.1. And the next layer has also decreased in thickness to about 0.2. So the next layer is 1.2, and to be like that. And then the next layer has gone from 0.3 to about 0.4, and the velocity is 1.3. And finally, the free stream has is like 1.4. So this is about 1.4, 1.3, 1.2, 1.1. So basically, the boundary layer has gone from the red profile to the green profile. Okay, so let's now look at how we characterize the boundary layer, right? What is the 3 boundary layer thicknesses of the green profile? Has it decreased or increased? So the easiest one to answer is, let's actually put up the numbers here. So this is about 0.6, right? Okay. What is the 99% thickness of the green boundary layer profile? Has it increased or decreased? Decreased, right? Decreased to how much? 0.6, exactly. Now this is the 99% thickness. So delta 99 of the green is now has decreased from 1 to 0.6, right? So delta 99 has gone from 1 millimeter to 0.6 millimeter. Okay, how about delta star? Delta star has gone from, initially it's about 0.31. Now is this green region, right? And this green region we can kind of count. There is this area is 0.1 times 0.3, right? And this area is 0.2 times 0.2, and finally this area is 0.1 times 0.3, right? And if you multiply and sum them up, that comes to 0.1, right, millimeters. And initially was how much? 0.31. So it's significantly decreased, right? Okay, and how about theta? So theta has gone from what, 1.71, 0.171, and again to now to compute theta, we need to do another multiplication. Oh, actually, sorry. I think I didn't do it correctly. So I just counted the area without normalizing, without the division. So again, let me just write the definition. Delta star is equal to integral 1 minus u over ue, right? I computed the ue minus u, so let me just write it in another form. So integral of u minus ue, not ue minus ue, but ue minus u divided by ue times dy. So that's the same as 1 minus u over ue, right? I think in this calculation, the first number is just the ue minus u, the difference between the free stream and between the edge and boundary layer velocity without dividing by ue. So after summing them up, I should also divide the whole thing by 1.4. So that's going to be even smaller than point than 0.1. So you can just 0.1 divided by 1.4, that's going to be 0.07. All right, okay, and then theta is going to be equal to u over ue multiplied by this, right, dy. So right, so what we do is for each of these numbers, we'll multiply by another u over ue, and then still divide by ue at the end. So let's do a calculation of 0.03 times ue equal to 1.3, right, plus 0.04 times 1.2 plus 0.03 times 1.1, the whole thing divided by ue squared. Okay, sorry, squared. Okay. That does not look like what I want to compute. Okay, let's go to Google. I think it's more reliable. Okay. So there are two division by 1.4, right? The edge velocity. One is all of these velocities should be divided by ue, and there is also divided by ue here. So it should be divided by ue twice. And I get 0.06. All right. Okay. So finally, let's look at how my shape factor has changed. My shape factor initially was 1.8, and that has changed to 0.07 divided by 0.06, right? Just of course, the number is not going to be very accurate, but like we know it has decreased by a lot. Okay, so this is a trend we see for boundary layers on the favorable pressure gradient. So all the thicknesses decrease, and the shape factor also gets much closer to 1 on the a massive favorable pressure gradient. Another thing is if we look at the skin friction coefficient, right? Particularly if we approximate the derivative du dy over here of the red one versus green one. The green one has a much higher velocity near the wall and has a much smaller delta y near the wall, right? As a result, the skin friction has increased or decreased? Increased, right? Skin friction also has increased a lot. So I don't have time to do this numerically, but CF has a massive increase on the after experiencing favorable pressure gradient. All right. So this is actually a general trend of how boundary layers respond to favorable pressure gradients, and the opposite happens on the adverse pressure gradient. So on the adverse pressure gradient, we have actually a slide afterwards. You can actually repeat the calculations. What we can see is that all the three boundary layer thicknesses, they increase significantly. The shape factor also increase, okay? And the skin friction decrease. And one particular situation for adverse pressure gradient is that now if you think about this pressure difference being, instead of pressure difference being negative, the pressure difference is positive, and all the left-hand sides now have to be negative, right? There is starting to be a point. If this is negative enough, then the velocity after experiencing the negative pressure gradient, the adverse pressure gradient, now can become zero, right? The layer most close to the boundary. When the velocity becomes zero, how would the thickness become of the bottommost layer? Infinity, right? And this can never happen. As the velocity, as you go downstream, as the velocity slow down to almost zero, thickness grows. And at some point, the boundary layer is not going to be like this anymore. The boundary layer is going to become like that, right? That's when flow separation happens. All right, flow separation happens when some velocity layers at the bottom of the boundary layer slows down to practically zero. Okay, that's what's going to happen. And if you work this out by yourself, in this, over here you can still see the trend, right? Over here you can see that things doesn't work out anymore. There are so much pressure now that when the flow slows down to this much, actually not on this slide. Like I didn't put it over here, but like if you suppose even a slower velocity, you're gonna see the boundary layer starts to separate, and you get negative velocities at the bottommost layer, which doesn't make sense anymore. All right, okay. So this is how boundary layers responds to pressure gradients, and in the next lecture we're gonna apply this knowledge to airfoils and see how things, how airfoils stall. And there is some particular trends, like, yeah, what do you think airfoils at different Reynolds numbers can achieve in terms of its CLmax? And it turns out there is a very strange curve that goes like that. And the best airfoils to get the CLmax at different Reynolds numbers look very different. So we won't be able to actually know quantitatively how to get to this, but like we'll analyze all of this and see like why, at least we can explain like why the airfoils has to be very different for different Reynolds numbers based on what we have learned. All right, okay, so see you on Friday.